Basically, from 2003 onwards, he is designated scientist on the scientific team of MARSIS, the radar on board the ESA Mars Express mission. So he's giving a presentation on a joint presentation, joint work, let's say, on development of procedures for using GrassGIS in planetary mapping.
Thank you, Marcus. Good morning, everyone. I will present the work done basically in my PhD for using GRASS in planetary mapping. Anyway, on the first talk on this morning, I was presenting my little contribution with the Python packages. Now we come into the problems I found. I try to explain you the complexity of the thing, how I've approached it. And so we are just talking about join two different communities. GIS has got techniques, has been out for almost 20 years. GRASS is an example of a big GIS problem project. And we will see that GIS can be useful to the planetary science. We will see also that that could be problems in using GIS on planetary for handling planetary data. These problems are not too big since GIS are currently used in planetary geology, for example. So, why joining two different communities, the planetary scientists that used to analyze the surface of the planetary bodies, and the GIS world that is a wide wide interest group of people, because at the end they are all interested in dealing with specially referenced data. So let's see how using GRASS, how adapting GRASS, using it in planetary data. And let's see if a mutual exchange of views can improve both the groups of persons. So I will present the procedures I've developed for using GRASS in planetary mapping. It is not standard, it is not a final product or so on. It is just a result of a study. So, why doing planetary mapping? Because studying the surface of the planets always required mapping of data. We see on the left a sketch of Huygens directly from 1659. And then on the right, we see just the first image from IRISE, that is a camera on NASA Mars Reconnaissance Orbiter, that will deliver, I think in November, images of the surface of Mars at a resolution of 30 centimeters. So, since the beginning, the problem was detecting data, taking data, and put it on a projection. In this case, we are dealing with a sort of orthographic projection. In that case, we are seeing just a projected image. And this data projected on the planetary surface serves as the base for planetary research. Another thing about planetary data is the fact that it has been delivered in a wide range of time, in a very large range of time. starting from the 60s, the Mariner and Viking missions delivered a lot of data that let us know that, for example, Mars had craters and not channels or streets. And then we are in the 90s with the Mars Global Surveyor that gave us a digital elevation model of Mars at the resolution at about 1 on 128 degrees per pixel at a resolution about 400 meters. And then there is the Mars Odyssey and the first European Space Agency mission to Mars, or planetary mission in general, but to Mars, Mars Express. And then we have MRO that is just starting to deliver data in these days. This data is a big importance for research and for knowledge in general. And how can we protect data? How can the scientific community can take care about the data? By making data available. In the 80s, all the large volume of data from Viking and missions tended to be very large in volume. And in the 80s, NASA talked about a method to archive planetary data in a smart way, we can say, because if we are dealing with a large volume of data, the problem is that even if the data we want is inside the archive, it can be almost unreachable. So they decided to put up the so-called Planetary Data System, or PDS. What is the PDS? It is a distributed system made by different, they call it nodes. And every node holds data for a specific subject. For example, there is the geoscience nodes that holds all the data, for example, from imagery, spectrometers of the surface of the planet. Going up in the time scale, in the 90s with the internet, the PDS was interfaced through the internet, on the internet with the planetary imagery atlas. So all the people, scientists or not scientists, were in the condition to analyze data or just see the data from Mars. On 2005, European Space Agency followed with the example of NASA, and he made up a planetary science archive that now is up and running. You can access data from Mars Express, and it holds data from planetary mission from European Space Agency. What is PDS at the end? It is a structure of archiving system, but it is also a format. All the data is held in PDS files, and a PDS file is a common document non-proprietary data format. It is well documented. There are tons of manuals to read, but it is good because it is a common format for all kinds of data. And in planetary mission, we have a lot of type of data models. Just think about a radar that can give you a slice, or, for example, a spectrometer that give you multi-spectral or hyperspectral data. So, after seeing PDS, let's see how system expressively built for planetary cartography has developed through the years. Starting from the 60s, so the Viking missions, JPL developed a VCAR processing system, and then USGS and JPL NASA were the center of development for planetary mapping expressly developed system. Arriving to the 90s, where ISIS was developed by the USGS. Starting from the first times, all these systems were specifically designed for planetary mapping, and they were dedicated systems. Let's see, in this case, we are in the, maybe in the 70s, 70s. And on the right, we see just the display system of the processing environment. Okay. The planetary imaging system and processing systems were specifically designed to deal with planetary data. So they were going to project data to clean data, to serve as image processor, basically. With GIS, the planetary data, in general, can be analyzed with new techniques that were developed for the Earth. Basically, I've selected the things that I think that were not available there in the planetary mapping world. We are able to compare different data sets taken by different missions in different time at a different resolution. That is quite difficult to do with a standard image processing program. We can use derivative maps. What are derivative maps? Since we are all keen with GIS, they are vector maps. Vector maps are not recognized by the image processing systems, since they are not the results of sensor reading. They are just interpretation, or they are just derived data product. And then use of RDBMS. For example, if we have a lot of data on a file, we have to access it. It can be time-consuming to access it sequentially. So the use of RDBMS can be useful for analyzing planetary data. Anyway, the use of GIS in planetary geology is not a news. Here we have a little review of what has been done with GIS. Since 1993, we have studies on Venus, then Moon in 96, Mars 97, and that was the time when we got higher resolution data, tons of data from Mars. And then from 2000, about 2000, USGS astrogeology program started to serve planetary data in GIS formats. GIS systems are generally usable off the shelf with projected planetary data. So basically, all the geologists, planetary geologists or scientists use planetary data that they were given in a projected system, so they are not having trouble with reprojection and so on. But since GIS systems were designed for the Earth, they are generally do not know much about planets. In particular, there is a general lack in spheroidal figures of the planet and satellites. So, for example, if you are working in a lat-long system and you are going to measure a distance, you need this not to be wrong. And then the second point is also important because there is a lack of generic support of cartographic reference system used in planetary mapping. This means that reprojecting data may be difficult or impossible. So we are just a step beyond the basic use of GIS in using in planetary data. Since we already have a community that uses GIS with planetary data that scientists give out in a GIS format. But since I just was studying to be a researcher, I needed the fresh data to be reprojected and to be analyzed together. So, let's see what are the cartographic reference systems used in planetary science or in planetary geology in particular. The International Astronomical Union is a group of scientists that every 3 years communicate each other the news, the advancement of science, and also they suggest reference system to be used. From the 70s, these are the two reference systems used in planetary mapping in general. We use the planetographic system. We are talking about body fixed rotating reference system, so the same we know as GIS. We are not talking about inertial reference system and so on. We are not going to land a spacecraft, land rover, or we are not involved in engineering. We are just involved in planetary mapping and analysis of maps. So we are dealing with cartographic reference system. So planetographic is the one we know, since planetographic system is a positive westward longitude system from 0 to 360 degrees. And for the Earth, we have minus and plus 180. Latitude is defined as the angle between the normal of the ellipsoid in a given point and the equatorial plane, as we know. Since in planetary science we are dealing with celestial mechanics, so we are dealing with spacecraft orbiting around planets, we are using, most of the missions use the planetocentric reference system. And so some maps are delivered with this cartographic reference system. Positive east longitude. Latitude is defined as the angle between the line connecting a given point and the center of mass of the planet and the equatorial plane. So planetographic latitude is different from planetocentric latitude. If you go on Snyder, 1987, cartographic projection, a working manual, the Bible of projections, these are all explained. Terminology. We are talking about planetographic and planetocentric for a general approach to cartographic reference system in the solar system bodies. To specify the planet, just substitute the prefix planeto with geo for Earth, for example, and we are with geographic reference system and geocentric reference system. For Mars, for example, we are with areographic and areocentric. For the Moon is selenographic, selenocentric. Just a thing to note for the good students is that if we are dealing with a sphere, these two systems coincides. But if we are dealing with an ellipsoid, and in our solar system, it is the case of the Earth and the Mars, we have a difference in these two latitudes. This is the case, this is the plot I made for the case of Mars with latest ellipsoidal parameters. And so we see here the latitude centric, so the aerocentric latitude from 0 to 90. And here we have the difference between the planetocentric and planetographic latitude. So if we are dealing with ellipsoids, and we do not check if we are dealing with planetocentric or planetographic latitude, we are going to have a difference. This difference at 45 degrees reaches about 0.37 degrees, that on Mars is 20 kilometers. So, in a planet where we have data at the order of 20 meters, the positional accuracy is about 100 meters. We cannot be wrong here. So, even if you are just working with projected maps and so on, we have to know that. So, let's go and see what has been developed. I had just to check what was the better system to implement all the needed procedures. A system that was portable, available, unlimited access to the source code, credible by the scientific community, and interoperable with existing system. The objective was to provide an ellipsoidal figure of the solar system bodies for obtaining a correct distance calculation, to provide O-centric O-graphic conversion tools for vector and raster maps, to have a PDS ISIS, that was the image processing from USGS astrogeology program data handling. GrassGIS was the system I chose because it is widely used by the industries and research institutions. It is written in C with scripting capabilities, and soon Python, as we see at E30. From 97, it is free software under GPL license, so we are the freedom to use, to distribute, to study, and to improve it. And it is available for almost all the computer architectures and supported by broad scientific community and literature references.
5 minutes.
5 minutes? Okay. So what has been produced? Data file for providing ellipsoidal figures of solar system planet satellites based on the International Astronomical Union 2000. C codes for projection of vector maps, raster maps, choosing the interpolation method between planetocentric and planetographic, and scripts for importing PDS data that is basically a binary data. These are the proposal from Planetary USGS astrogeology program to use APSG codes for dealing with the coordinate reference system of solar system planetary bodies. The code definition is the APSG code is equal to PDS naive code, so the internal code of the PDS system, multiplied by 100. So for example, Mars for a planetary scientist is 499 planet, is the planet with ID 499. And then the APSG code is 49900, so we have 100 slots to get local projection on that planet. So we can start now. Yes, of course, a text file with APSG code has been produced, so we can start GRASS and specify the APSG code of the planet, for example 49900, that is the spheroidal definition or so on. And then after that, we can import data. Data import is through this is an example of multispectral image. We are working with cubes where spatial data and spectral data is put into a cube. Good news, from GDAL 132 we have support for ISIS cubes, and this is very good. Anyway, we can work with RNGDAL, RNBean to import PDS data. So let's quick view an example of using this kind of procedure in GRASS. What I used sources from different era, from different mission, from different institution. I use European Space Agency, Mars Express, high resolution stereo camera imagery, multispectral. the geologic map from USGS astrogeology program, and the topography from Mars Global Surveyor MOLA MEGDR at the resolution about 400 meters on Mars. This is the study area. We see the topography in orthographic projection of Mars. We are studying, I've been studying this last summer, a plane just in the northern part of Mars. We see these beautiful channels. There is no water actually there, but we are studying that part of the planet that is very interesting. And so let's see the topography of Mars into grass. Actually, the zone is not the ideal screenshot, but we can see craters there, and also these features that are ghost craters, very interesting to study. Anyway, this is the topography inside grass. Let's go with Mars Express high-resolution stereo camera imported into grass. This is Chryse planitia, a part of the study area. And we have all the bands, the 3 RGB bands and the infrared band, and we can inspect with the inspect the spectral signatures with grass, and we see the application. And then the geologic map, vector map, directly from USGS astrogeology program. Every area has got a link with the database inside grass, and we have the name of the formation, the area measured in sinusoidal projection, and the unit symbol that for geologists is the fingerprint of the geologic unit. So finally, let's see all the data aggregated into the same monitor of grass. This is the topography, this is the multispectral imagery. Let's see how it fits over the topography, and these are boundaries of geology. So this is the result of using different data sets projected into the same reference system, and this data can be used to make analysis with GIS techniques that I not show here because it is what is going to made by any one of you. So conclusions, data from different instruments, from different missions can be analyzed together in GrassGIS. Using this conversion of any map, raster, and vector data or any ellipsoid, these are results of my study and must be validated somehow. I'm just interested to talk about that with a lot of scientists. So if you are interested in this stuff, just contact me, I will be happy. EPSG codes have been written into a file. I will, I think, or publish or put into Grass or talk with Frank how can be accessible. So with these codes, we can play around with the planetary bodies around without making gross distance calculation errors. And then I provide some script from PDS data into Grass. And as I told you, GDAL 1.3.2 has got ISIS-2 version, ISIS-2 driver, so we can import with GDAL planetary data actually. Future work, aesthetics. So for example, on dgrid and PS map, implementing the different reference system and so on. And of course, I have to work on documenting the work and publish and get validation by the scientific community. Thank you.
Thank you very much. So we don't have too much time. Maybe one question while the new presentation is set up.
Could you give us an idea how large the open source community within the planetologist community actually is? Except from you, for sure.
Yeah. Here I am. Here I am.
Nobody else?
No kidding. I think that there are many people interested generally in open source, but I think in recovering a sane communication system between scientists, between different scientific interests. So, for example, these procedures are copied in almost 1,000 programs around for space agencies. So having it in a common base where we can discuss, it is a good thing. So there are people interested in it. Thank you.
Okay, thank you very much.